Let us now discuss about the lattice structure of FIR filters. Let us take up a problem. Draw the lattice structure of FIR filter with system function h of z equals 1 plus 2z inverse plus 1 by 3 z power of minus 2. Now, the given system function can be compared with the general system function of FIR, and we can obtain the coefficients to be A0 which is equal to 1, A1 equals 2, A2 is equal to 1 by 3. Okay, so from this we observe that the highest power is equal to minus 2, or the order is 2. Now here in the solution now we depict the same coefficients but slightly in a different way. Okay, now we use the notation as A2 of 1, A2 of 2 and probably A2 of 0, where 2 indicates the order. So the order is second order here, so we indicate the order as 2. So we know here that the first coefficient will be called as A2 of 0, which is equal to 1. A2 of 1 is the second coefficient here, and A2 of 2 is the third coefficient. Okay. Now, we indicate the order here as capital M. So capital M is equal to 2, which is the order, or we know in this equation we will have 2 zeros. Let us understand the process of direct form to lattice conversion. Okay, so the direct form to lattice conversion involves a formula which is given by for small m is equal to starting from m minus 1 till the very last term, which is 1. So for order 2 we will have m which is 2 comma 1. Now for these values of small m we have to evaluate the equations which are given below. The equations are Km is equal to Am of m. Km is called as the lattice coefficient, and A here stands for the direct form coefficient. So we are having a link between the two, and Am minus 1 of 0 is equal to 1. Am of I is given by Am of I minus Am of m, which is same as Km, so this can be written as Km also, into Am of m minus I, whole divided by 1 minus Km square. This equation is evaluated for different values of I, which ranges between 1 to m minus 1. So this is the formula that we used to obtain the lattice coefficients. So the process starts by considering the m value which is equal to 2, and then we evaluate these individual equations. So let us see the process now. First we begin taking the value of m which is equal to 2. The first equation, on substituting Km, that is K2 is equal to A2 of 2, and we are aware that A2 of 2 from the given data is 1 by 3. So we stated K to be the lattice coefficient. It's also called as the reflection coefficient. Next, for the second equation, here, we are having m is equal to 2 already. The value of I has to be considered. Now we know we start with the value of I which is equal to 1. So with m is equal to 2 and I is equal to 1, let us substitute in the above equation. So since m is equal to 2, 2 minus 1, it gives you 1. So we have A1 of 1 is equal to A2 of 1 minus A2 of 2 into A2 of 1, m minus 1, it is 1, divided by 1 minus A2 of 2 the whole square. Now if it is possible to simplify, we can simplify, or straight away if you want you can do substitution, and then also you can do simplification. So here we see that A2 of 1 is common, so we take A2 of 1 common, and in the bracket we have 1 minus A2 of 2. Then in the denominator we have 1 minus A2 of 2 into 1 plus A2 of 2, if it's in the form of a square minus b square. Then this term will cancel off, and what remains is a2 of 1 by 1 plus a2 of 2. And we know what are the values. a2 of 1 is equal to 2, a2 of 2 is equal to 1 by 3. Substituting and simplifying, we get the answer is 6 by 4. Further, that can be written as 3 by 2. So we have computed what is called as a1 of 1, which is equal to 3 by 2. So let us just check, have we tried it for all combinations of I? The value of m we are aware is equal to 2. Okay, we know that the value of m is equal to 2. That means that the I should lie in between 1 and m minus 1. So m minus 1, 2 minus 1 is equal to 1. So for m is equal to 2, we have exhausted all the cases. Let us proceed now by taking m value, which is m minus 1. That is m is equal to 2. 2 minus 1 is 1. So this time a small m will take a value which is equal to 1. Similarly, the first equation will give you k1 is equal to a1 of 1 is equal to 3 by 2. And similarly, actually we can continue for the second equation, but honestly speaking, our requirement was to find the lattice coefficients k1 and k2. Okay, k1 and k2, and we have done that. So there is no point in proceeding with the calculation. So we have got the result. I think it is sufficient. Okay, we don't have to continue with the calculation part. So at this stage, we should be able to write the structure now. We should be able to write the structure. Let us draw the structure. Okay, to draw the structure, we shall start from the input end. We have x of n as an input. This x of n is passed through a couple of lines. One of the lines will have a delay which is z power of minus 1. The other line will not have that particular delay. Okay, and we have learned about these reflection coefficients. So these reflection coefficients is what is used to perform the scaling. Okay, the scaling is done using reflection coefficient. So this is the structure, this is the arrangement that we say is called as lattice arrangement. Okay, now here we have to note that the scaling is performed by a value which is called as k1. Okay, so we have taken the signal from here. Okay, we have taken the signal from here. Both these signals are scaled by the value called as k1. So this is the first stage. Okay, so order is 2. We'll have 2 stages. Similar second stage is drawn. Once again, remember, one of the lines has a delay, the other does not. Okay, the other does not. Again, we take the signal output and we add it here. We take the signal from here, we add it here, and please don't forget we have to scale it. Okay, we have to scale it. So scaling here is done with k2. Here we scale with k2. And the output that you get from here, okay, the output that you get from here is called as y of n. Okay, output you get from the top is called as y of n. Okay, so just as a notation, if we want, we can select the notation here. Let's call it as f0 of n. This can be called as f1 of n. This can be called as g0 of n. This becomes g1 of n. And this output is called as g2 of n. Okay, so this corresponding output may be called as f2 of n, but we know that is the final output, hence it is termed as y of n. So this is how you write the structure, and the values of k1 and k2 already we are aware. K1 and k2, they are equal to, k1 is 3 by 2, the k2 value we know is 1 by 3 from the calculation. So this is how you write the lattice structure. Let us take a look at the next problem. An FIR filter is given by y of n is equal to x of n plus 2 by 5 times x of n minus 1 plus 3 by 4 times x of n minus 2 plus 1 by 3 times x of n minus 3. Draw the lattice structure. Now, once again, we note down what is given. The given difference equation we copied down. Next, taking Z transform on both sides. When you apply the Z transform, the result of Z transform will be something like this. Z transform of y of n is y of z, x of n, Z transform is x of z, 2 by 5 times capital X of z into z power of minus 1 plus 3 by 4 x of z in capital z power of minus 2 plus 1 by 3 x of z into z power of minus 3. Now from this we can collect all the terms with x of z and we can collect all the terms with y of z in it. Therefore, gathering the terms, we can obtain the ratio of y of z by x of z. Okay, so we take x of z common and we bring it down here, and what remains here is 1 plus 2 by 5 z inverse plus 3 by 4 z power of minus 2 plus 1 by 3 z power of minus 3. Okay, this is the system function. This is a system function. Now from the system function we can determine the coefficients. Now clearly we see the highest power is 3, z power of minus 3. So we can call it as a third order system. The order is 3. Therefore, in this particular problem, we identify that A3 of 1 is this coefficient. It's equal to 2 by 5. A3 of 2 is equal to 3 by 4. A3 of 3 is equal to 1 by 3. So these are the three coefficients, okay, which we can identify apart from the first coefficient. Okay. Here we are aware that the filter order which is indicated as capital M is equal to 3. The M value here is 3. That is, in our problem we are going to solve it considering the value small m. As we know, small m is m minus 1, m minus 2 till the last value 1. So here we start with the highest value, which is m, next minus 1, next minus 1 of that. So the possible values of m for which we have to solve is 3, 2 and 1. And we are aware of the formula, the equations that we are going to use. We are aware of those equations. Let us write down those equations again and then proceed for the substitution. Now, we know that Km, reflection coefficient or the lattice coefficient, is Am of m. We know that Am minus 1 of 0 is equal to 1, and Am minus 1 of I is equal to AM of I minus AM of M into AM of M minus I, whole divided by 1 minus AM of M the whole square, or it is simply called as Km square. Okay. Now this is to be verified considering the value of I starts from 1, 2 and so on. The last value, highest number, is going to be M minus 1. Okay. So M we are going to select in the beginning and we are going to adapt that same value of M. I think now we can start with the substitution part. So in the very first step, we are going to take the M value, small m should be equal to 3. Okay, we'll take M value equals to 3. Step 1 is performed for M value equals 3. Therefore, the first expression Km, okay, K3 is equal to AM of M, A3 of 3. We know from the given data it's equal to 1 by 3. So one of the coefficients is already obtained. Next, the second equation, it says AM minus 1 of I, AM minus 1 of I value I have to determine. Okay, so we just write the equation. Next we have AM of I minus A3 of 3 into A3 of 3 minus I whole divided by 1 minus K3 square. This is after inserting the value M in the given formula. Now for this, the value of I that you can have is between 1 and M minus 1. So when you take M minus 1, we get the value as 2. So the possible values of I to be solved are I is equal to 1 and I is equal to 2, keeping the M value as 3. So let us start. Therefore, when you take the value as 1, so we are considering now M value is 3 already and the I value is 1. The equation now becomes A2 of 1 equals A3 of 1 minus A3 of 3 into A3 of 3 minus 1, it's 2, divided by 1 minus K3 square. Okay, the next part would be substituting the values. Okay, so we can substitute and then simplify. This is 2 by 5, this is 1 by 3 multiplied by A3 of 2 is 3 by 4 from the data divided by 1 minus 1 by 3 the whole square. So here we take whole square. Okay. We have to perform the simplification of this, and on simplifying you will get the value 8 minus 5. The common denominator here you can take is 20. Okay, just a minute. So we have to perform the simplification. You may use calculator. So solving, we got the answer for A2 of 1 as 0. We got the answer as 0.169. Thank you all.